Welcome to lesson 14 of industrial instrumentation. In this lesson, we will continue with the flow meters. As I told you repeatedly before that the number of flow meters are huge in number. So, we have to continue on several lessons and you have to discuss in details all the flow meters. So, in this lesson basically we will cover the one open channel meter, which is very widely used for irrigation purposes, that is wear, and also we will discuss a direct electrical output flow meter, that is turbine flow meter, right. So, let us look at the contents of this lesson. Flowmeter 3 as it happened. Now, we will have contents. So, we will first discuss the wears, its principle, its application, what are the different types of wears, that also we will discuss, and then we will discuss the variable reluctance tacho generator, because using that principle we will make the turbine flow meter. Turbine flow meter advantage is the direct electrical output. So, in many applications it is popular, and moreover it is unlike differential pressure flow meters. We do not need any conversions and square rooting, all those problems are not there in this type of flow meters. We will also discuss the turbine flow meter. Now, at the end of this lesson, obviously the viewer will know that how to use a wear in the systems. I mean, how the person can use a wear for measurements of water flow, especially mostly it is used for water flow in an open channel like canal or duct, right. That means principle of operations of open channel meter, that is wear. Open channel meter we have already discussed that not only wear, we have actually pitot tube is also used, but pitot tube, as you know, it is mostly used for the gas, and it is not suitable for the dirty liquids, because when you are talking of the measurement of the flow of water in a canal or river, you cannot expect that it will be very clean. So, it will be extremely dirty in that sense. So, we need some other rugged flow meters. So, in that sense there is no other alternative than wear to use the measurement of flow in open duct, I mean open channel, right, like canal, river, like that. So, we will also look at the magnetic pickup, because this magnetic pickup you will find that we will use in many applications, measurements of velocity and all these things. So, the principle is same, whether I suppose if I want to know that an RPM of a motor, so that can be utilized, the magnetic pickup is also used there, and also if I want to know the liquid flowing in a pipe. So, what is the liquid flowing in a pipe if I use some magnetic pickup? So, that is also, I mean, that is a part of the turbine flow meter. That is the reason we will discuss magnetic pickup also. Also, the turbine flow meter with direct electrical output. So, these three things we will discuss in, the viewer will know the details of these three components. Now, let us look at the wear. Wear, you see, it is an open channel meter first of all. That is I told you repeatedly, it is an open channel meter, it is not a closed channel meter. Now, if the flow rate of a liquid in an open duct or channel such as a river or canal is required, a wear can be used. There is no other alternative, as I said, it can be used, but in fact actually there is no other alternative than using wear. It is extensively used to get an estimate of flow of water in a canal or duct for irrigation purposes. Okay. So, whenever there is irrigation, so how much water is to be given to a particular land and all these things details, these estimates is only possible by if we use wear, right. So, it is very much suitable for measurements of the liquid in open, it is not for gas. So, it is only for the liquid and mostly for water. And principle of operations of wear, and moreover one thing I forgot to tell you, that it is, you see, it does not depend on the temperatures and all those things. Many other sophisticated, as you know, there are many complicated flow meters are there. So, but it does not depend on temperature. Suppose if the water is coming out of a boiler, if I want to measure, if you are discharging that water somewhere, So, that type of measurement is also possible in by means of wear, because if the temperature increases, it hardly matters to wear, or the flow coefficient also does not change much. You see the flow rate excuse me, the flow rate over a wear is a function of the wear geometry and the wear head. You will see that basically there are two types of wears used. One is rectangular wear and is V notch wear. Usually the rectangular wear is used for the large flow measurements, and the V notch wear is used for the low flow measurement. And however, you will find that the V notch wear is actually more accurate than the rectangular wear. In this particular lesson, so we will discuss or we will derive the flow velocity as well as the volume flow rate for in the case of rectangular wear, but we will give the expression for the volume flow rate whenever we are using the V notch wear. Anyway, so it depends on the wear geometry, right? Geometry and wear head. What is wear head? Let us look at. The wear head is defined as the vertical distance between the wear crest and the liquid surface in the undisturbed region of the upstream flow. So, this terms we will use repeatedly, the undisturbed region of upstream flow. So, it looks like this, we will discuss, we will see here. If I take a blank page, you will see the wear actually that is a restrictions like, see it is a restriction like this. We will give the figure. So, water is flowing through this side, okay, there is a channel, right. So, water is flowing from this side, right. So, if it is closed on this side, suppose, so liquid will flow over this one, right, this. So, this is called the crest of the wear, right. If you look at it, I mean if I take a side view, it will look like this, sharp edge. So, water is falling over this liquid, right. So, this is the in fact actually I mean you will see that this will be like this one, that means I have a, if I take a side view. So, the water is falling, so falling like this. So, this is our undisturbed region of the upstream, right. So, this will be our H, which will be shown in the next figures, right. So, here if I take the velocity V1 and at the crest if I take the velocity V2, then we can easily write the Bernoulli's equations, right. Our goal is to measure this height H, okay, by any means. So, what are the different means that I will show you later on. So, by measuring H I can calibrate this instrument in terms of flow, that means H can be calibrated in terms of flow, and mostly it is indicated type of instruments or monitoring type of instrument, it is hardly used for transmission purpose, right. So, that is I am saying the wear head is defined as a vertical distance between the wear crest and the liquid surface in the undisturbed region of the upstream flow, right. The schematic of a wear is shown in figure 1, the rectangular wear is shown in figure 2, and flow of liquid over the sharp edge of the wear is shown in figure 3. So, in subsequent 3 slides we will find that we will show you the wear geometry and rectangular wear and flow of liquid over the sharp edge of the wear. So, these are all in figure 1, 2 and 3 respectively. Now, you see that there is a schematic of a wear as I shown you. So, this is a duct, assume that this is a river or a canal. So, the liquid is, if I take a different pen, liquid is flowing in these directions, right, and flowing out in these directions. So, restrictions we have put like this, right. So, in a Collins dictionary you will find the meaning of the word wear is basically dam, but actually it looks like a dam, I mean restrictions, but so there is a, as it happened in the case of dam, there is a level of difference in the upstream and the downstream. The similar thing is here also, right. Let us look at very carefully. You see this is our crest of the wear, right. liquid is coming here and falling down, right. Now, if I put a float on this side which can move only in the vertical direction, then what will happen, this according to the, if the flow velocity is high, so this height will go up, right, is h. If you look at h, because liquid is, suppose the liquid is in this up to this level, right. So, from the crest to the undisturbed water level, that is the h or head of the weir. I repeat that from the crest, that means the sharp edge of the weir to the level which is undisturbed water level is a capital H, that is the head of the weir. Actually, we will measure h, right, by some means. So, this is a schematic of weir. Now, you see this is a rectangular weir. So, this is we will discuss later on what is small h, what is dh. So, this is our crest of the weir, right, and this is the water level. Not necessarily it will go to the top, right, water level may go up to this position. In fact, this should be not up to this, this should be it should end here, right. So, this is the water level, this is h, right. So, from this crest to the upstream undisturbed upstream water flow level, that is the capital H, not this part, right. And for derivations later on we will see, we take a small section dh at a height of h, right, from the top of the undisturbed flow level, okay, undisturbed flow level upstream, that is we are taking. So, at a distance h from the undisturbed upstream flow level, we take a section, we work with dh. This will be needed for later on to find the total volume flow rate or volumetric flow rate in the rectangular weir, right. Now, let us look at the how the weir, how the water flowing on this weir, where h is head on the weir as we told, and L is the length of the weir, is basically length of the crest of the weir, and small h is the distance below the free surface of the water where V2 exists. That will be shown in a more clearly in the next slide, right. You see here, yes, it is clear now. You see this is the upstream undisturbed region of the upstream flow, right. This is the water level, this is the undisturbed region of the upstream flow. If I take a plane, this is the undisturbed region of the upstream flow. So, this is everywhere, this is same, because water is coming like this one. So, this level, so it is undisturbed. So, after that you see water height start to fall, right. Now, in the previous slide, if you see what we have seen, okay. Here you see what will happen, let us go back. Anyway, so this is the distance h, okay. In the previous slides, you see here h is a we have taken a section of small section dh of height dh at a height from the undisturbed region of the upstream flow of h. That means, if you look at, so this is our h, this is from the upstream, okay. This is the from the undisturbed region, right. Fine. Now, see what will happen. So, this is h and the velocity above the crest is V2 and velocity upstream is V1, clear. If it is there, so I can immediately, so this sharp edge is very important, we will discuss later on, because if it is not sharp, the calibration constant will be modified. So, you can usually after a certain months we can just change the wear, keeping all other dimensions constant, so that the our flow coefficients will remain same as before. Let us look at clear. Now, if I apply the Bernoulli's equations at a undisturbed region of upstream flow and at the crest, that means the sharp edge of the weir, we can immediately write H plus V 1 square by 2 g, capital H minus H plus V 2 square by 2 g, is not it, because the height is, if I take from the datum level. So, it is H minus small h, right. If I go back, you see H minus small h, at these positions my V 2 exists and H is exists. So, in that case we are taking this one as a datum level, is not it. You see, this is we are taking as a datum level. So, this is H height plus V 1 square by 2 g. So, at this one is V 2 square by 2 g plus, if I take this one as a datum level. So, it is H minus H where V 2 exists, is not it. So, if it is there, so I can write these equations. You can, interestingly, you can see here that all are dimensions of height, because if this is in meter, so this will be meter square plus second square. So, g is meter per second square. So, obviously, it will be in meter, clear. So, no problem in that side. So, dimensionally it is correct, right, where V 1 is the upstream flow of the liquid and V 2 is the flow at the crest of the weir, that we have told once we have shown you the diagram. So, obviously, if I manipulate the equations, so the equation number 1, so it will come up as V 2 equal to, because this H and H will cancel out, V 2 equal to 2 g H plus V 1 square by 2 g, right. Now, in most cases you will find that the V 2, the speed at the crest will be always very large, that we have seen. Those who have visualized near the dam, you will find that whenever in a lock gate especially, you will find that when the water is flowing over just above the lock gate, the speed of the water is very high compared to the calm upstream flow, right. So, in that cases, so I can obviously tell that the V 2 will be much higher than the V 1. In that case, what will happen, you see, we can simplify these expressions like this. If V 1 is small compared to V 2, then we can write V 2 equal to root over 2 g H, right. This is equation number 2, right. However, the ideal flow rate, if I want to now find the ideal flow rate, because this is a velocity because it is not very easy to measure the H, right, because this the we are getting the flow at the crest. So, it is please remember another thing, whenever it crosses the if I take a blank page, it is easy to understand. You see here what will happen whenever the liquid, I have a crest here. So, if I take some other pen, so you see here, so here the velocity is V 1, so liquid is falling down, here is V 2 at the crest, right. So, here you see that again the velocity will reduce. So, at this position only the velocity will be high, this velocity will not be maintained. Once it falls down, the velocity will also be reduced in this region. It is already less than V 2, here also this velocity will be less than V 2, right. However, the ideal flow rate over the weir is obtained by integrating the quantity V 2 into dA. What is dA? Over the area A of the flow plane just above the crest of the weir. What is dA? Let us look at. What is dA? You see, dA is actually, we are finding dH multiplied by L, that is the dA. So, dH multiplied by L will be the dA. So, we will integrate over the height H. Okay. So, we will get the total flow velocity. If I come down here, okay. Now, you see, so theoretically what we can write, that if I go back, so however the ideal flow rate over the weir is obtained by integrating the quantity V 2 into dA, velocity at the crest multiplied by the dA. dA is a small h sections at the height h from the top, small h of width dH. So, dH into L will be the dA over the area A of the flow plane just above the crest of the weir, right. So, we can write Q theoretical, that means theoretical volume flow rate equal to V 2 into dA. So, it is meter cube per second, because this velocity is meter per second, it is in meter square. So, if I convert, so it will be 2 GH, right, root over 2 GH, already we have seen, multiply by what is dA? LdA, that I told you earlier. So, this will be equal to integrated over, instead of A will be from, since it is all converted, L is constant, only H is variable. So, we have converted this integration varies from 0 to H. So, if I do it, so I will get the expressions equal to 2 by 3 under the square root 2 G into L H to the power 3 by 2. Please note it is H to the power 3 by 2. This is equation number 3. Now, however, this is as it happened in all flow meters. So, we see that every time we have to multiply by a flow coefficient, sometimes we call flow coefficient, sometimes we call discharge coefficients. So, it is sometimes very difficult to measure, actually to find theoretically the value of all the discharge coefficient. Best thing is to find experimentally with some standard flow meters, right. So, however, as it happened in any other flow meter, the actual flow rate is less than the ideal flow rate due to the vertical contraction from the top and the friction loss and the presence of the liquid flow that is not horizontal. Therefore, the actual flow rate is given by. So, vertical contraction, this is slow contraction from the top. If you look at, you see here, so there is a slow contraction from the top, right. I have a weir. So, there is not that suddenly it is coming. So, it is a slow contraction from the top, and we are assuming that all flow velocity is like this, like if I have weir, we are assuming that the all velocity is in this direction. This is not necessarily true. Velocity will be in this direction, some velocity will be in these directions also, right. So, you have to take care while we are making the, if we are interested to find the actual flow rate, right. For that reasons we are telling you, see how the actual flow rate is less than the ideal flow rate due to the vertical contraction from the top and the friction loss and the presence of the liquid flow that is not horizontal. Therefore, the actual flow rate is given by Q actual equal to C D Q theoretical 2 by 3 square root 2 G C D L H 3 by 2. This is equation number 4, where C D is the discharge coefficients of the rectangular weir, and it lies between 0.62 to 0.75, and the wear must be sharp for this coefficient to be valid over a long period of time before the flow meter is recalibrated, right. This I told you earlier also. That means, this H should be very sharp, otherwise what will happen, you will see that this the calibration constant or discharge coefficients will be modified. That happens in all the instruments, okay. Most of the instruments, like you see in the case of venturi, when we discuss the venturi meter, in the case of venturi meter this type of calibrations is not necessary. But we have seen in the case of orifice meters, this if the edge is not 90 degree rectangular orifice, you will find that the discharge coefficients will be modified. So, best way during the routine maintenance, you change the orifice. If you know the thickness and everything is same, dimension is same, the orifice hole diameter is same, you do not have to recalibrate, right. Similar in the case of discharge coefficients or in the case of wear also. So, during the routine maintenance of suppose after using 1 month or so or 2 months, depending on the how much is the corrosions in the water and all these things, we can just change this wear, and it is not very expensive equipment. That is also you must mention, I mean this to be this to be explained, because it is not expensive compared to the, I mean if you look at the other open flow meter, it is not very expensive. So, in that sense it is replacing a wear is not very expensive affair, right. So, when the flow rate is low, now we talked about the rectangular wear, but there is another type of wear, as I told you, this is called V-notch wear. When the flow rate is low, a triangular or V-notch wear is more suitable for measurement of flow. This type of wear is more accurate than the rectangular wear, right. It is for the low velocity flow rate, but it is more accurate, right. A V-notch wear, as you can see, is shown in figure 4, right. You see here also. So, this is the length of the V-notch wear, okay. This is also restrictions, instead of rectangular, this type of where will be put it, and so this is slowly increasing. This is the included angle theta. As before, we have taken a section dH, okay, from the top of on the undisturbed flow region H, and H is the head of the weir. Okay. As the liquid flow increases, this head will increase, go up, H will increase. Please note, because in the previous case also we have seen that this H has increased, right. So, total excuse me, the ideal flow rate for V notch weir is given by Q theoretical equal to 8 by 15 under the square root 2 g tan theta by 2 H to the power 5 by 2 4 L by 15 H, if I replace tan theta by 2 under the square root 2 g H to the power 5 by 2, this is equation number 5, where L is the width of the weir or length of the weir or width of the weir, whatever you say, it is same thing, right. So, it looks like this, you see. We have seen that anyway, you see here. So, this is included angle theta. So, tan theta will be how much? Tan theta will be L by 2, this total is L. So, it is L by 2 divided by H if I take tan theta. So, exactly that thing I did in the next slide. So, tan theta by 2 is replaced by L by 2 divided by H. So, it will get 4 by L 15 H root over 2 g H 2. So, L is the width of the weir. So, what is the variable here in the Q theoretical also? You see H, as the liquid flow volume flow rate increases, H will increase, right. The height or head of the weir is increased. This H is to be measured by some means or the other, right. All other things are constant, L are constant, G is also constant. So, it is quite non-linear, okay, as you can see. So, this H is to be measured and this height is calibrated in terms of the volume flow rate. However, the actual flow rate, as it happens in the case of the rectangular weir also, you will find the actual flow rate will differ from the theoretical flow rate. So, it is to be multiplied by a discharge coefficient C D 4 L by 15 H. So, under the square root 2 g H to the power 5 by 2, equation number 6, where C D is the discharge coefficient that lies between 0.58 to 0.6, because this is experimentally found. It is very difficult to find the theoretical value of C D. So, what the people did, they have taken some standard and then they compared and found the C D value. Now, equations 4 and 6 indicate that the flow rate of the liquid depends on the height on the head capital H, right. So, that capital H is to be measured. What is the capital H? That is the upstream height of the upstream flow from the crest of the weir, right. What is that? Very clearly, let us look at H. I have to measure some or the other. What is that? That means I have a liquid is flowing, right. So, I have a liquid flowing like this one undisturbed. So, this H is to be measured. As the flow rate increases, this H will increase. If the flow rate decreases, this H will decrease, right. Clear? Even though it is nonlinear relation, but if the flow rate decreases, this H will decrease. If the flow rate increases, this H will increase, right. So, I will measure the H and calibrate it in terms of the flow rate, fine, right. Now, as I told you earlier also, you see the weir head is measured by a float activated displacement transducer and it is placed in the upstream side, and it is usually used as an indicating instrument. It is not for the transmitting instrument. People tried though but it is not for the actually it is indicating or monitoring instruments. Usually what they do, you see in the upstream side, so they are making a, sometimes they are making a float like these ones, right. So, one like these ones. So, there is a, it is put on a cylinder, right, transparent glass, okay. These are actually spheres, which acts as a float. So, what will happen? So, this is put on the upstream side, right. What will happen if the water level increases? So, this float will go up, this float will go up like this one, right. This float will go up like this one, and if you have a graduated scale here on the glass itself. So, I can measure this height and calibrate it the height in terms of flow. So, these are basically for balancing. If you use single, that means the problem of balancing. So, they use three actually if you take a top view, three spheres like this one, okay, 120 degree apart, three spheres made of plastics, okay, and put a if I take top view you cannot say. So, it is like this one, right. So, if I take a side view, it will like this one, three spheres. So, one float. So, as the liquid, I mean if the flow increases, this will go up. So, this is calibrated in terms there. So, this is all about the wear. Now, wear, as I told, there is no other alternative for irrigation purpose for making the, and it is quite robust. It is not that accurate obviously, but it is get an estimate of the flow of the fluids, especially in the irrigations purposes, right. Now, our next transducers which we will discuss is the basically we will discuss the turbine flow meter, which is direct electrical reading flow meter. But to know the turbine flow meter, we must first look at the variable reluctance tacho generator and what is the some basic terminology of the reluctance and magnetic force we must tell in brief, and its units in SI. Then we will go for turbine flow meters. First we will look at the variable reluctance tacho generator, because exactly that principle is used to make a flow meter. So, let us look at magnetomotive force. Magnetomotive force is a force that causes flux to be established, and it is analogous to the electromotive force for electric circuits, right. The unit of MMF, we write magnetomotive force, we write MMF in SI units is the amperes. Is actually ampere turns, but it is actually telling about the single turn, but it refers to a coil of one turn, right. The opposition to the establishment of magnetic flux is called the reluctance. So, reluctance, whenever reluctance increases, your flux decreases, if the flux increases, reluctance decreases, right. So, the reluctance is defined as R equal to MMF, magnetomotive force, divided by the flux phi, right. Rearranging, I can write MMF equal to R multiplied by phi, right, where MMF is in ampere turns if the number of turns is more than 1, and phi is the flux is in Weber. Now, principle of operations of this variable reluctance tacho generator, let us look at. If the time varying flux phi linked by a single turn of coil, all of you know this is the basic principles, then the back EMF developed in the coil can be expressed as E equal to minus d phi by dt, right. Here you can see the variable reluctance tacho generator shown in figure 5. You see this we are showing a wheel with teeth or blade, whatever you say. Okay. There are several teeth you can see, or blade, several teeth here, and this wheel is made of this teeth actually is made of ferromagnetic material. Please note, this is made of ferromagnetic material, and a coil is wound on a permanent magnet, and this pole piece is made of soft iron. So, what is that? This coil is wound on a permanent magnet, this pole piece is made of soft iron, and this teeth is made of ferromagnetic material. Now, you see what will happen, there is a flux will be developed, is not it? How it looks, you see the flux will be go like this one. Sorry, if I take a new page, I think I should go back. So, if I take some other color, I think let me choose this color. So, the flux will look like this one. So, it is go like this, go like this, go like this, go like this in this direction, is not it? Then what will happen? You see what will happen, that when this teeth or blade comes to the very close, actually this gap is very small. So just for sake of understandings, we have drawn in such a larger gap. In theoretically this actually in the variable reluctance tachogenerator, this gap is very small. Then what will happen? In this case, whenever it comes to very close to this, reluctance will be small, flux will be high, and in between the teeth, suppose this wheel is rotating in a direction in a anti-clockwise directions with a angular velocity of omega. You see this one, this is your angular velocity, wheel is rotating with an angular velocity of omega, right. Now, what this angle is theta. What will happen? You see, if this rotates, if the wheel rotates like this one, right, then what will happen? If it rotates, so whenever this wheel in between the two teeth, suppose the teeth has gone down this direction, this has moved to this, now this pole piece faces the gap in between the two teeth, then what will happen? Reluctance will increase. So, there is a change of magnetic flux, right. So, what will happen? This output voltage, there will be variable output voltage, okay, time varying output voltage will get if it rotates with the speed of omega, right. So, using this principle we will find we have made a turbine flow meter. So, here again I will repeat, this is made of permanent magnet, right, and this pole piece is made of soft iron and this teeth is made of the ferromagnetic material. Now, the teeth of the wheel moves in close proximity to the pole piece. It is very close to each other, as I told you, because for the sake of understanding we have drawn that much of gap, but it is actually there is no gap. This gap is very small, right. This gap is ultimately there is no gap at all. So, it should come very close to this, right. This will come very close to this. That means, if I take it, so this will come very close to this, right. That you please note. So, it should come very close to this like this one. Anyway, so the teeth of the wheel moves in close proximity to the pole piece, as I told you. Therefore, the flux linked by the coil changes with time and the voltage is developed across the coil. The total flux phi subscript capital T linked by a coil of m turn is given by phi t equal to m phi m mmf into divided by r. R is the reluctance, number of turns of the coil is m. So, it will be given by m into mmf by r. Moreover, we know that when the reluctance is minimum, the flux is maximum and vice versa. So, that I have to explain to you already. The variation of the flux phi t with the angular position theta of the wheel will be expressed as this. We express, since it is sinusoidal variations, we can express is phi t theta equal to alpha plus beta cos n theta. Okay, what is this abbreviation? Let us look at, where alpha is the mean flux and beta is the amplitude of time varying flux and n is the number of teeth of the wheel. If there might be 4 wheel, there might be 4 teeth, there might be 8 blade. Okay. So, here in this case we assume that the number of teeth is n. So, we can write phi t theta is time varying theta, total flux with respect to the angular position of the wheel is equal to given to alpha plus beta cos of n theta. Clear? So, E, the output voltage which will received at the coil, is given by minus d phi t by dt, total flux equal to d phi by minus d phi t by d theta into d theta by dt. That always we can write, is not it? So, again we know that a d phi, if I differentiate my previous expressions, that means if I differentiate these expressions. So, I will get, if I differentiate these expressions, I will get d phi t by d theta minus alpha will cancel, alpha d alpha by d theta is 0. So, minus beta plus into n into sine of n theta. Now, theta is a omega is a circular frequency and theta is an angle at an instant of time. So, if you multiply it by omega by t, I will get theta, obviously theta should be in radians. So, d theta by dt equal to omega. Quite obviously, if I differentiate this with respect to t, I will get omega. So, I will substitute all this in the equation in these expressions, right. In these expressions, I will substitute this value of d theta, d phi t by d theta and d theta by dt, I will substitute in these expressions. So, I will get, where omega I should say is the rotational velocity of the wheel. Now, E equal to beta n omega sin n omega t. What does it mean? It means you see that the output voltage from the variable reluctance tachogenerator, okay, is a function of the angular frequency amplitude of this. It is sinusoidal signal, okay, the output voltage. If it rotates at a constant velocity of circular frequency omega, that means the wheels rotates at a constant velocity of circular frequency omega, then you will find that output voltage is expressed as beta n omega. So, this is very important expressions. So, I should right. So, what is the amplitude? Amplitude is beta n omega of this output signal and with the frequency of n omega. That means, I can say the amplitude of this signal. So, that means, I will get an output voltage if it rotates at a constant angular velocity beta n omega and the frequency, this amplitude, that means A, and frequency is equal to n omega by 2 pi, is not it? I mean linear frequency. So, output voltage depends on both. Okay. So, later on we will see that we will make some little manipulations of the or little signal processing by which I want to make that output voltage will be only proportional to the frequency of rotation, that the frequency increases or output voltage also increases. But here it is not, because if the frequency increases, amplitude also increases, if the flow velocity, if the number of rotation increases, number of the wheel rotating which that is increases, this omega increases, your output voltage also increases, but does not depend directly only on omega. Here amplitude increases, here your frequency also changes. So, two are changing simultaneously, that is not very desirable properties, right. Now, in turbine meter exactly this principle is utilized, right. This principle is utilized in turbine meter. You see what will happen, it has a direct electrical output. This is a great advantage in the other flow meters. We have seen that we have to make lot of manipulations of the signal processing we have to do, like differential pressure flow meters, rotor meters. We have seen that there is a lot of pitot tubes, or we need a different lot of signal conditionings. Sometimes it is not signal conditioning circuitry in that sense, it is a electrical. Sometimes you will find this pneumatic signal is coming, you have to convert with DP transmitter, and so many things are necessary, which is not necessary in the case of this type direct electrical reading meter. No, it is not much in use because of some disadvantages. Anyway, it has a direct electrical output. The flow meter consists of a wheel with a multiple blade. Now, I am telling here blade because the shape is like a blade in the case of turbine meter, but the blade whatever I am talking now, it is similar, exactly similar to the teeth in our wheel of the just discussed variable reluctance tachogenerator, right. So, there is no distinction between the blade and the teeth, please note, and it is installed inside the pipe in which the clean fluid is flowing. This clean fluid, the term clean is very important, you see it should be clean, liquid should be clean, otherwise there is a problem, okay, that we will discuss later on. So, the flow meter consists of a wheel with the multiple blade and it is installed inside the pipe in which the clean fluid is flowing. A schematic of turbine flow meter is shown in figure 6. Okay, we will show you the turbine flow meter. You see this is our turbine flow meter. So, we have a magnetic pickup. What is that magnetic pickup? This is a permanent magnet, okay, on which their coil is wound. In fact, there should be a 2 terminals should come out. So, 2 terminal will come out, right. These 2 terminals will measure the voltage E, right. What is this inside the magnetic pickup? This is a magnet. Okay. So, these blades are made of ferromagnetic materials. We have shown the 4 blades, right. 4 blades. You see these are in angle, little angle. So, when the flow is the liquid is flowing, it is impinging on the blade, Okay. If its impinges on the blade, so this will start to rotate. If it start to rotate, then what will happen? If it is angle is like this one, if it is like this one, then what will happen? And if I take the camera like this one, you see here, see if the blades is slightly like this, like it happens in the case of, so liquid will flow over this one, right, in this direction. So, what will happen, you see here in this direction, so it will start to rotate, right. So, similar thing. So, this is made of ferromagnetic material. I have magnetic pickup here. What is that magnetic pickup? Is made of permanent magnet on which the coil is wound with soft iron pole pieces. Since it is ferromagnetic material, whenever it rotates, for each rotations of the, whenever this blade pass this permanent magnets, I will get a pulse, okay, at the output, or I will get a time varying signal at the output. So, that will be calibrated in terms of the flow, right. Let us look at the details of this one. The turbine meter must be installed along an axis parallel to the direction of the fluid flow in the pipe, right. The flow of the fluid past the wheel causes it to rotate at a rate proportional to the volume flow rate. Okay, it should be proportional to the volume flow rate. The wheel or blade of the meter is shown in figure 7. You see this little bit, this each wheel causes an angle of alpha, right, angle of alpha, and you see here the wheel actually, if I take from the along the axis of the pipe, the wheel will look like this one. These blades will look like with the thickness T, and it is as an angle alpha. Okay, it is actually, it looks like this. So, it will have an angle like alpha, like this one, right. So, this is angle alpha, right. So, the water or liquid is flowing like this one, it is hitting this blade. So, it start to rotate in these directions, right. Construction, you see the construction of a turbine flow meter is made of similar to variable reluctance tachogenerator, no difference. The blades or teeth are made of ferromagnetic material. Magnetic pickup consists of a coil wound on a permanent magnet. A voltage pulse is obtained at the output of the pickup whenever a turbine teeth or blade passes the pickup coil. As I told you, the flow rate can be determined by measuring the pulses by a pulse counter. So, if I can measure by a pulse counter, I can measure the flow rate, as simple as that. Moreover, I can find the total volume flow rate if I count the number of pulses over a certain period of time. That is a great advantage of the turbine flow meter. That means the total volume of liquid flown over a certain period of time. Theory: if a number of rotation of blades per second is f and the volume flow rate is q, then we can obviously write f equal to k into q. So, the q can be determined by measuring f. The total volume of liquid V t flown through the pipe over a given time t will be expressed as V t integral 0 to t q dt. The total number of rotation of the blade over the time t is expressed as n t. Now, we have total number count we have expressed t to 0 f dt k q dt into, so it is coming k v t, right. So, q dt, so we are getting k v t, right. The total count is proportional to total volume flow of the liquid. Okay. Obviously, this we can measure by some counter. So, which will give you the total volume flow of the liquid, right. The voltage induced in the magnetic pickup will be periodic in nature, whose frequency is proportional to the angular velocity of blades, right. So, assuming the drag force due to bearing and the viscous friction negligible, the rotor angular velocity omega is proportional to the volume flow rate given by, obviously what will happen as the volume flow rate increases, the velocity increases, obviously the omega also will increase. Omega depends on what? Omega depends on the velocity of the fluid flowing through the pipe. So, in turn, if I multiply it by the area cross section of the pipe, so obviously I mean minus the area taken by the hub and all these blades and all these things, I will get the flow velocity, angular velocity. So, I can say that the angular velocity will be proportional, angular velocity of the turbine flow meter is proportional to the volume flow rate. So, that is actually we have written. So, the velocity of the fluid is given by u equal to q by a, right. A is the area of cross section. Now, you see where a is the area of cross section of the pipe minus area of cross section of the hub, and area of the blades. So, that we have written pi d square by 4 minus pi d square by 4 n h minus d by 2 into t. So, this will be very clear, you see here. As you can see from the from the constructions, this will be very much clear. Okay. You see here. So, this is h. H will be not exactly d by 2. Please note, h is not exactly d by 2 because there is a gap. There should be some gap to because we have to give some space to rotate, right. So, this is our expressions we have shown pi d square by 4, the total area of cross section of the pi minus that the half, the area taken by the half minus the area taken by the blades, right. So, all these things if I, so where n is the number of blades and t is their average thickness. So, moreover we have seen that omega h by u equal to tan alpha by, in fact omega h equal to tan alpha, is not it exactly. So, omega h is the velocity of the blade tip because that is a circular cross section, is circular frequency multiplied by h is the velocity of the blade tip, and is because h is the actually if you look at h is the height of the blade from its central position, is not it. So, if I multiply by the omega, so it will give the speed of the tip of the blades, right, per second. The velocity of the blade tip perpendicular to the directions of the flow, obviously that will be very much clear because the liquid is flowing in this direction. So, the blades is rotating in this direction. So, if the direction of flow is this, the blade will rotate in this direction. So, I can write that alpha is the inlet angle and A at the tip. So, K 1 equal to omega by q tan alpha by A h, right. So, the output voltage from the magnetic pickup will be given by beta n k 1 q sin n k 1 q by into t, equation number 7, where beta is the amplitude of the angular variations of magnetic flux, n is the number of blades and q is the volume flow rate. The equation 7 indicates that the output of the magnetic pickup is a sinusoidal signal of amplitude beta n q and the frequency is n k 1 q by 2 pi, where which can be written mf into q, where m is called the static sensitivity or the meter factor of the equipment, right. Now, you see one thing you must note that if I look at here, if I look at in these expressions, you will find this will say again this is the expressions what we are getting. You see that it depends on the frequency of number of sorry, it is beta is depends on what are the factors q. As the q increases, this amplitude is also increases. Q is the volume flow rate increases, amplitude increases. The simply what they do actually they take a, if I take, I have a turbine flow meters, if I take a sorry. So, they take a meter, then they pass through an integrator, our turbine meter, then integrator, okay. Then a Schmidt trigger. What will happen, you see, once you integrate, I will get a signal which depends, I will get a constant amplitude signal, okay. I will get a signal which looks like this. You see, here I will get a signal, this output of the Schmidt trigger is a constant amplitude signal, because Schmidt trigger is a pulse shaper, as you know. So, I will get a signal that depends only on the frequency, okay. As the, that means as the flow velocity q changes, okay, here both the amplitude of the signal also will change, here it will not, because integrator this amplitude will cancel out, flow will cancel, the q is will cancel out. So, at the output of the Schmidt trigger I will get the only the frequency. So, the constant amplitude frequency I will get. So, that frequency can be calibrated in terms of the volume flow rate. Let us look at, let us go back again. So, that is actually they do in the case of meter. So, provided that the turbine wheel is mounted in low friction bearings, the measurements of accuracy can be as high as plus minus 0.1%. It is less rugged and reliable than the restriction type differential pressure flow meter. The blades and the bearings can be damaged if solid particles are present in the liquid. This is the most important part, liquid should be very clean, right. There is another problem, it is more expensive and it is also impose a permanent pressure loss on the measurement systems, even though it is not as high as because we are putting some restrictions in terms of the blades and all these things. So, extra pumping is here also. Okay. So, it is not that it is totally open channel, like it is not totally the permanent pressure loss free flow meter. So, there is a some certain amount of permanent pressure loss in this type of flow meters. So, the typical range is usually 10% to 100% of full scale output rating, and below the 10% of the full scale rating the bearing friction makes. Turbine meters are particularly prone to large errors when there is a significant phase change in the fluid being measured. Turbine meters have a similar cost and the market share to positive displacement meter, and the former are similar smaller and the lighter than the latter. Okay. Now, this is the some advantage, but as I told you in the turbine flow meter, the basic principles that I am getting an output, the flow velocities which I am getting is I am getting a sinusoidal signal at the output of the turbine flow meters, since the basic principle is the tachogenerator. So, as the flow velocity changes, amplitude changes as well as frequency of the signal also changes, frequency of the sinusoidal signal. Now, if I pass this signal through an integrator, then what will happen? So, this will cancel out. So, I can explain this again. Let us go back. You see here, yes, here you see here what will happen. So, if I integrate this signal, then what will happen you see. So, I will get beta n k 1, if I take a different color please don't. So, beta n k 1 q cos of n k 1 q into t divided by this n k 1 q. So, this n k 1 q will cancel out. So, after the integrations I will get E equal to beta cos of n k 1 q into t, is not it? See here, right. I will write it clearly, E equal to beta cos of n k 1 q into t. So, what does it mean? It means that you see that beta is a constant, it does not depend on the flow velocity. So, amplitude is directly proportional to the frequency. Now, what will happen? I will pass that signal after integration, I will pass that signal through a Schmidt trigger, I will get a constant amplitude pulses, but the frequency will change as the flow velocity changes. So, if I measure that frequency will be calibrated in terms of the flow, right. This is the advantage of this type of meters. So, with this I come to the end of the lesson 14.